We're now going to get into the meat of this electricity portion of this unit and talk about circuit analysis. We've learned a bit about electrical quantities like resistance, potential difference, and current. How do we use those now to analyze a circuit? But before we get into that, we'll have to understand a little bit more about resistance. And what we need to know is it possible to simplify a resistor network? So here we have two resistor networks, and that's just resistor network basically just means a circuit with a series of resistors, or a circuit with a number of resistors, because they could be in series or parallel. On the left we have a series resistor network. On the right we have a parallel resistor network. And the question is, what happens? What's the difference between connecting resistors in series and parallel? Can we just add them together, whether they're connected both ways? Does that work that way? And if we add these together, does it create a single resistor, or can we consider it as a single resistor in terms of circuit analysis? And what is that value of that equivalent resistance? Well, if we have a series circuit, the sum of R1 plus R2 plus R3 is equivalent to the total resistance, or the equivalent resistance of the circuit. So that's a rather simple equation there. RT is equal to R1 plus R2 plus R3 plus R4, or however many resistors we have, if they're connected in series. So here's a question. It says we have a 16 ohm light bulb, a 27 ohm heater, and a 12 ohm motor, all connected in a series circuit. What is the total resistance of that circuit? And in this case it's just 16 plus 27 plus 12. 55 ohms is the R equivalent, or the R total. Another question here. It says two identical unknown bulbs are connected in series with a 48 ohm and a 64 ohm heater to produce an equivalent resistance of 150 ohms. What is the resistance of each bulb? So now we'll have to do a little bit of an algebraic analysis here. Essentially what this question is saying is our RT is equal to a resistance of our with a 48 ohm and a 64 ohm heater. Okay, so let's call this RH1 for the heater, RH2 for the other heater. And these are two equivalent identical unknown light bulbs. So RL for light bulb, but there's two of them. So we have to solve for RL. That's the same as RT minus RH1 minus RH2 divided by 1/2. So 0.5, RT is 150, RH is 48. This is 64 for RH2. So our calculator here, we just simply do 150 minus 48 minus 64 times 0.5. Each light bulb has a resistance of 19 ohms in that case. So we looked at series connections. What about parallel connections? Now this one's a little bit more complicated, and I'm going to give you a different equation to use for this, because I don't like this one that they have here. But the idea here is that the reciprocal of the total resistance is equal to the sum of the reciprocals of each individual resistance. And that, when we get to the slide that summarizes all this information, I'm going to give you a different equation to write down. But I'll show you how to use the equation that I prefer for this question. Question number 3 here. So what we have is 1 over RT equals 1 over R1 plus 1 over R2. That can be rewritten as RT to the negative 1 is equal to R1 to the negative 1 plus R2 to the negative 1 to the negative 1. So there was this, sorry, I should get rid of that. RT is equal to R1, the reciprocal of R1 plus the reciprocal of R2, and reciprocating that sum. That's essentially what we're doing here. The opposite of a reciprocal is applying a exponent of negative 1 to it. So because R1 is a reciprocal, we can write that as negative 1. R2 is negative 1. If we reciprocate this side of the equation, we can reciprocate that side of the equation. So we can write RT equals R1 to the negative 1 plus R2 to the negative 1 and the whole thing to the negative 1. So why do I prefer this method? I think it's easier to enter in your calculator. And in this case, it would be written as 4 to the negative 1 plus 8 to the negative 1 to the negative 1. Lots of calculators nowadays have a reciprocating button, and I will show you how to use it in this case. You may have a reciprocating button like this, or you might have an x to the negative 1 button, but they're both the same. Here we have bracket 4 reciprocated plus 8 reciprocated. Close the bracket, reciprocate that, and we're left with 2.67. RT, I think we should round, we're really given only one significant digit, so let's just round to 2.7 ohms as our solution. And I'll move that calculator out of the way so you can see that. Here's another question. It says we have a unknown resistor connected in parallel with a 30 ohm and a 40 ohm resistor, and it produces an equivalent resistance of 15 ohms. So what is the resistance of the unknown resistor? So we know RT equals R1 to the negative 1 plus R2 to the negative 1 plus R3 to the negative 1 to the negative 1. To find this unknown resistor, we can isolate for that, R3. So we move the negative 1 to the other side. RT to the negative 1 equals R1 to the negative 1 plus R2 to the negative 1 plus R3 to the negative 1. We isolate for our unknown, which I'll call R3 in this case. So R3 to the negative 1 equals RT to the negative 1 minus R1 to the negative 1 minus R2 to the negative 1. And then we reciprocate that. So RT to the negative 1 minus R1 to the negative 1 minus R2 to the negative 1 to the power of negative 1. And this, we substitute, it's going to be a total resistance of 15 to the negative 1 minus 30 to the negative 1 minus 40 to the negative 1, whole thing to the negative 1. And let's find out what our R3 is. Turn our calculator on. So we have bracket 15 reciprocated minus 30 reciprocated minus 40 reciprocated, close the bracket, reciprocate our solution, and we have 120. So R3 is equal to 120 ohms. So here is the equivalent resistance in series and in parallel. You can copy this down, but for the parallel equation, I'd like you to also copy down the other equation that we use, and I'll turn on the camera just to show you what I think you should have in your notes. So equivalent resistance in parallel is RT equals R1 to the negative 1 plus R2 to the negative 1 plus whatever else we have, all to the negative 1. That's our equation that we can use. You may want to pause and copy that down, because I think that works better, especially with calculators that have a reciprocal button. So far we've talked about series and parallel circuits, but most circuits are actually going to be mixed circuits. They're going to have portions that are in series and portions that are in parallel. And here's an example of a mixed circuit. You can see that R1 and R5 are connected in series, but R2, 3, and 4 are all connected in parallel. So how do we analyze a circuit like this? The equivalent resistance is actually a lot more useful in a situation like this, because now we can simplify this complex resistor network into an equivalent resistance, and we can use that equivalent resistance to find the total potential difference or the total current of the circuit. So let's look at these two resistor networks. The first one is a rather simple series connection. It's simply just the total resistance is 20 plus 40 plus 60. The second one is a parallel network. So I'll use our calculator just to solve this, but it's the reciprocal of 20 plus the reciprocal of 20, and that answer reciprocated. So 20 reciprocated plus 20 reciprocated equals, and we find the reciprocal, we get 10. So what about these more complex networks? And I'll show you how to add these together using our R total, and I'll show you a new symbol you might not know, but the parallel add symbol. Let's turn the camera on and let's move this up so we can see these resistor networks. So for 5C, I can add this. I know that I start with 60, and 60 is connected in parallel with actually both 20 and 10, but 20 and 10 are connected in series. So my RT is going to be R1 parallel added to R2 plus R3. So my RT equals R1 to the negative 1 plus R2 plus R3 to the negative 1 to the negative 1. So here's how I would add these together. 60 reciprocated plus 20 plus 10 reciprocated. And let's move this over a bit so we can turn our calculator on. You can see the calculation. So here we have bracket 60 plus bracket 20 plus 10. Reciprocate that. Close the bracket, reciprocate. We end up with a total resistance, an RT, of 20 ohms. So 5D is RT equals, and we start with R1 parallel added to bracket R2 plus that's a series addition to R3, which is parallel added to R4 plus R5. So altogether, we're going to have this 60 parallel added to our 45 plus the parallel add between 30 and the series add between 10 and 20. I know it looks a bit complicated. You could break it into steps if you'd like, but we could also do it this way, which may kind of help your understanding. So R1 to the negative 1 plus R2 plus R3 to the negative 1 plus R4 plus R5. This is to the negative 1. To complete this parallel add, we have that to the negative 1. And to complete this series add, we have to close the bracket. And then to complete the final parallel add, we have another negative 1. So our RT, we are going to have 60 to the negative 1 plus R2, which is 45, plus R3, which is 30 to the negative 1, plus R4, 10 plus 20. This is to the negative 1, to the negative 1, to the negative 1. So all of those reciprocals we'll be able to solve for this on our calculator. And just before we do the calculation, let's count our brackets to see if we're good here. So we have one open, so 1, 2, 3, 4 open brackets, 1, 2, 3 closed brackets. So a mistake was made here. Let's figure out what that is. Well, this 45 is supposed to be series added. So this closed bracket here is my add between the 30 and the 10 and the 20. I need to have a closed bracket just before that, and then another closed bracket with the reciprocal. So now let's try this out. So bracket 60 reciprocated plus bracket 45 plus bracket 30 reciprocated plus bracket 10 plus 20, close the bracket, reciprocate, close the bracket, reciprocate, close the bracket, close the bracket, reciprocate. So let's add this now. We have bracket 60 reciprocated plus bracket 45 plus bracket 30. That's reciprocated. Plus bracket 10 plus 20. Close that. We reciprocate that. We're going to close the bracket and reciprocate. Then we're going to close the bracket between the 45 and the 15. That's the 60. So we're going to reciprocate that. Close the bracket and reciprocate. And we're left with 30 as our solution. So you could also break this in parts if it helps. Breaking it in parts, you'd see we have 10 plus 20 is 30, and then 30 reciprocated plus 30 reciprocated is going to be 15. So that means that if we look at this here, where we see that 30 branch here, that becomes a 15. 45 plus 15 is 60, and then we just do 60 reciprocated with 60, and then we reciprocate again, we get 30. So you can break it up too if that helps. But I do prefer doing it all in the one step, just because that's how I'm used to doing it. But when you're still learning, it might be good to break it up in parts. Let's now move on to the next portion of this lecture. Just a second here. Okay, so calculate the equivalent resistance for this circuit. And this one is a little bit easier to do. We have an R1 and R5, and we have R2, 3, and 4 all in in parallel. So let's move it up to the top here. Turn our camera on. Down a little bit so I can see. Okay, so our R total in this case, for number 6, is going to be R1 plus bracket R2 parallel added to R3 parallel added to R4 bracket plus R5. And that's going to equal 12 plus bracket 75 to the negative 1 plus 50 to the negative 1 plus 30 to the negative 1 to the negative 1 plus 18. So let's determine what that would be. We have 12 plus bracket 75, 50, 30, close the bracket, reciprocate, plus 18. Our total is 45. And that's how we would add that one together. So with what we've learned about electricity, you should now be able to do a complete analysis of any simple circuits, parallel or mixed electric circuits containing resistances. However, because so many different electric circuits are possible, there's no standard approach to analyzing a circuit. The steps to take in each case will depend upon the information you have about the circuit and what you need to find. In most cases, you could use KVL and KCL to find 2 of V, I, or R, and then you can use Ohm's law to calculate the missing value. In some cases, you must first reduce the circuit to a single equivalent resistance, and then find your source current or your source voltage. So here's a full analysis question. We have our full circuit here, and we need to solve for this, all of the missing values. So how I like to start with one of these questions is by first, let's turn this on here. We'll write down what we need to solve. So I1, V1, V3, I3, V2, I2, and R2. That's what we need to solve for here. And we'll fill in these as we do our work to solve them. So I'm given no voltages for each of the resistors, and I'm given no current for each. But I can find my RT using Ohm's law. RT is VT over IT, and in this case RT equals 120 over 12. So RT is 10 ohms. So knowing that, I can now try to solve for my unknown R2, because I also know that RT is equal to R1 plus the parallel addition between R2 and R3. And let's write this out and then rearrange. R1 plus R2 negative 1 plus R3 to the negative 1 to the negative 1. We need to isolate for R2 in this case. So we have RT minus R1 on this side of the equation. R2 to the negative 1 plus R3 to the negative 1. I can reciprocate both sides of the equation. And now I need to isolate for R2. So R2 to the negative 1 is equal to RT minus R1 to the negative 1 minus R3 to the negative 1. And then I can reciprocate that side. Then I can write my answers in, or my substitutions in. RT is 10. R1 is 8. R3 is 3. So let's do this in our calculator here. I'll make this easier. I'm just going to say 10 minus 8 is 2. So bracket, bracket, 2 reciprocated minus 3 reciprocated. Close the bracket and reciprocate. I have an R2 being 6. And then I write my R2 solution here. So now that I have my R2 value, I can go back and start looking at solving more information. So the R2 and R1, that makes one loop. So for that loop, my voltage has to be 120. I don't know the voltage of either at this time, so I can't really work with that. Let's see if I can work somewhere else. Let's look at the current. I have a current of 12. That's going into the junction where I2 and I3 split. I1 is equal to I12, or 12 as well. So now I can solve for my voltage for R1. So V1 equals I1R1. That's going to be 12 times 8. I'm just realizing I could have done this at the start too. This would have made it a little bit easier. 12 times 8 is 96. So 96 volts is my solution for V1. I may not have needed to solve for this to find out the rest, because now that I know that that's 96 volts across R1, using the idea of Kirchhoff's voltage law, if I drop 96 volts there, I have to drop the remaining volts at R2. So V2 is equal to VT minus V1. That's going to be 120 minus 96. So that will be 24. And I also know that because V2 is equal to V3, V3 is also equal to 24. So I can fill in 24 volts and 24 volts here. Next, now that I have those, I can use the Ohm's law to find for the other values. V3 equals I3R3, or I3 equals V3 over R3. So I3 would be 24 over 3. That would equal 8 in this case, 8 amps. I3 equals 8 amps. And now knowing, I guess we could have filled in this from the start, that's 12. Knowing that we have 12 going into the junction where I2 and I3 split, I can subtract those to get my final solution. I1 equals I2 plus I3. I2 would equal I1 minus I3. So I2 equals 12 minus 8. I2 equals 4 amps. And that's my final solution here with everything. That's my full analysis of that circuit. What about this circuit here? So here we're showing resistors as lamps. The concept is still the same though. Let's find all of the missing values in this circuit. I need to find these values. Let's write them all down. V1, R1. Sorry, V1's already known. I1, R1. Actually, there's two V1s. I think they're trying to say I total. So I total, R total. It looks like V2, R2. And I3, R3. I4, R4. I5, R5. So a big list of these here. So let's work on these. First, what I'd like to do is just look to see if there's 3 known values in any of these here, and I don't see that as the case. So we then need to let's start with Kirchhoff's voltage law. I have 40 volts to drop across a loop, and if I follow the loop of V5, V4, V3, and V1, I can see that my VT has to be equal to V1 plus V3 plus V4 plus V5. So my unknown value V1 is equal to VT minus V3 minus V4 minus V5. So V1 equals 40 minus 5, 10, and 15. So all together, that's going to be V1 equals 10 volts. So I know my first value, 10. Using my understanding of the current, Ohm's law, I can find R1 because I1 is known. So R1 equals 10 over 5. That's 2 ohms. Next, so I fully solved that one. I could then use the V1 and my V5 to solve for V2, because using Kirchhoff's voltage law, Vt also equals V1 plus V2 plus V5, and V2 would be Vt minus V1 minus V5. So V2 equals 40 minus 10 minus 15. And that gives me 15 volts. So V2 also equals 15 volts. Now let's use the Ohm's law to solve for what's remaining for our resistor 2, which is the resistance. R2 equals V2 over I2. R2 equals 15 over 3. So R2 equals 5 ohms. And I can fill in 5 ohms here. Now, I've done quite a bit with using the voltage law. Let's use the current law to do some more analysis here. I1 is 5, and part of that branch is resistor 5. So I1 equals I5, which equals 5 amps in this case. So my I5 equals 5 amps. And that helps me find R5. R5 equals V5 over I5. So R5 would equal 15 over 5. And that equals 3 ohms. So I can fill in 3 ohms here. So I need to now analyze 3, 4, and the total. Well, if I know 5 amps is going into that junction, then I know that at that junction, let's say I3 equals I4, and let's just call it I34, because it's the same. At the junction where we split into I2 and I34, we are going to have I1 equaling I2 plus I34. So I34 is equal to I1 minus I2, which is equal to 5 minus 3, or 2 amps. So for both 3 and 4, I can write in 2 amps. Now I can use Ohm's law, I'll do it over here on the side, to find out what my R3 and my R4 are. R3 is V3 over I3, which is the same as I34, so that's going to be 5 over 2. So R3 is 2.5 ohms. R4 is V4 over I4, which is 10 over 2. So R4 equals 5 ohms. So let's fill those in. R3 is 2.5 ohms. R4 is 5 ohms. We just need to solve for IT and RT. Well, IT is going to be 5 because that's the I1 is equal to IT. We can write that down here. I1 equals I5 equals IT. And then we can solve for RT because VT over IT would be the same as RT. So VT is 40 over 5. The total resistance of this would be 8 ohms. And we can solve, or we can finally put this in here, 8 ohms. And that is our full analysis with all of our solutions there. Quite a bit of work, but not impossible. We're given another mixed circuit, and I'll go through this as well. So for this one, let's see what we have to solve for to start. So I see that there is a, I don't know why it's labeled as a 1, but I'm going to call it VT. VT and RT are unknown in this case. Moving on, I have I1 and R1 being unknown values. For 2, I have V2 and R2. For 3, I have I3 and R3. And for 4 and 5, I have I4, R4. 5, we have V5 and R5. So these are my unknown values, so I have to do a full circuit analysis of this. Just a second here, let's get it to zoom in. Okay. So what I have to do now is I know my current total. Let's see if I can use what I know from that current total to start here. So IT is 6, and it would be equal to the current in I1 because they're both part of the same branch. So we can start by saying I1 is 6 amps. That's our first step because they're part of the same branch. Next, I can use Ohm's law to find out what R1 is. 36 over 6. It's going to be 6 ohms. So my R1 is 6 ohms as well. So we have one resistor or lamp fully analyzed. We can now use that to help us solve others. Let's see what we can do here. The current going through the junction where we split to 4 and 5 is equal to I total or I1. So I4 plus I5, their sum has to be the same, and I know I5, so I4 must be IT minus I5. I4 equals 6 minus 4 equals 2 amps. So my I4 is 2 amps, and you can use Ohm's law to solve for the remaining. So voltage at 4 is given to us as 16 over 2, so that is 8 ohms. So R4 is 8 ohms. my voltage across V4 has to be equal to the voltage across V5 because of Kirchhoff's voltage law. So I can now state that V5 is 16 volts. And that can help me find R5 because V5 over I5, 16 over 4, gets me to my voltage for R, which is 4 ohms. Now we just have 2 and 3 to look at, and then the total resistances and voltages. For V2, I know the I. I don't know the I for the third resistor there. So I know that I1 has to equal I2 plus I3. And because I need to solve for I3, I write that as I1 minus I2. That is going to be, I1 is given to, or sorry, we solved it already as 6. I2 is given to us as 2. So we have 4 amps for I3. Using Ohm's law, we need to solve for R3. V3 over I3. V3 is 20. I3 is 4. We've calculated it. So we have 5 ohms. Sorry, I did that all off to the side there. We have 5 ohms for R3. So we can go back to our list. R3 is 5 ohms. Next, we have to solve for V2, and V2 is the same as V3 using Kirchhoff's voltage law, so we know that this is 20 volts as well. So we can write down V2 is 20 volts. We can calculate R2 using Ohm's law, V2 over I2, which is 20 over I2, which is 2. So we have 10 ohms. So R2 is 10 ohms. Now, we can solve our total resistance by doing the sum of everything. Or we can solve our total resistance using Kirchhoff's voltage law, which I think is a bit easier. So let's follow the voltage along one of the loops, since we know all the voltages. V1 plus V2 plus V4. That's our total voltage. So VT equals 36 plus V2, which is 20, plus V4, which is 16. So 36 plus 20 plus 16. I'm just going to use a calculator because I'm doing a lot of math today. 36 plus 20 plus 16 is 72. So we have 72 volts. For our total voltage, we can write that up here, 72 volts. And then our RT equals VT over IT, which is 72 over 6. And 72 divided by 6 gets us to 12. So our total resistance is 12 ohms. We now have our full solution set in a fully analyzed circuit. All right. Here is another problem. It says complete each circuit given the by finding unknown quantities indicated. Oops. In these cases, you'll need to find the equivalent resistance first. So there's one where I solved it where I found the equivalent resistance, but there was an easier way to do it. Here, we're going to find our given values, but we don't have enough information to do anything with them unless we find the equivalent resistance. So let's start with the first one here. our values we need to solve for, and I'll move this fully over here now so you can see. The values we need to solve for are I0, or IT is what I'm typically used to calling it, I1, I2, V1, and V2. And if you notice, we don't have enough information to do Ohm's law anywhere. If we try Kirchhoff's voltage law, we have 2 drops and a 6, so we don't know exactly what's been dropped across each one. And we can't use Kirchhoff's current law because there's no current that's given. So first we have to find the total resistance. So RT equals R1 plus R2. And in this case, that's going to be 5 plus 7, which is 12 ohms. Next, we can find IT. It's going to be VT over RT. And that works out to 12 over, sorry, not 12. It's going to be 6 over 12. 6 over 12, which is 0.5 amps. So my IT is 0.5. Because of Kirchhoff's current law, I know my IT is equal to my I1 and my I2. So 0.5 amps, 0.5 amps. And then I can use the 2 different Ohm's laws to calculate for V2 and to calculate for V1. So V1 equals 0.5 times R1, which is 5. V2 equals 0.5 times R2, which is 7. So in both cases, we have 2.5 volts and 3.5 volts. If I add those two together, I get 6, which means that my answer is correct. So that's my fully analyzed circuit, where I have to do a equivalent resistance first to analyze it. Next one, here's a parallel circuit. So here we're asked to solve for, let's write down what we need to solve for: V1, V2, IT, V1, V2, IT, I1, and I2. And this is actually more of a an authentic type of question or application, because you would know your voltage applied because you usually set that, and you would know your resistors by placing them in the circuit, but you won't know exactly what, there won't be any readings for how the electricity will interact with that circuit that you have. So in this case, these are a bit more authentic in terms of doing electronics engineering. So here, to start with, we need to find our RT, which is R1 parallel added to R2. So RT equals 6 to the negative 1 plus 3 to the negative 1 to the negative 1. That is going to equal 2 ohms. I'll let you do that on your own. Now that we know the RT, we know that we can find our IT, and that's equal to VT over RT, 6 over 2. So our IT is 3 amps. That 3 amps is going to have to split across branch 1 and branch 2. But we could state that, actually we didn't have to find the equivalent resistance, because we could have solved this using Kirchhoff's voltage law. Just looking at it here, VT is equal to V1, which equals V2. I just looked at it again and noticed that. That means that each of those are equal to 6 volts. So that is a 6 volts and a 6 volts. So if I know that that's 6 and 6, I can find the current through each. I1 equals V1 over R1. So 6 divided by 6. It's 1 amp going through I1. And then I know the other one's going to be 2. But I could have solved it in 2 different ways. This is going to be 6 divided by 3, 2 amps. So sometimes I go into solving for the equivalent resistance, but you could also just look at it a little bit more and you might be able to determine that you don't need to solve the equivalent resistance. Because that is kind of a big step.